this session as well as to DRIEMS Autonomous. We are very glad that sir has given his consent to attend or deliver this technical talk to the participants. Welcome to DRIEMS, sir.
Thank you.
Dr. Sanjay Kumar Parida is presently working as Associate Professor in the Department of Electrical Engineering, IIT Patna. He has completed his PhD in Power System Group in the Department of Electrical Engineering, IIT Kanpur, in the year 2009. During his PhD program, he was awarded the Senior Research Fellowship by Power Management Institute, NTPC Limited, Noida, in the year 2007. In this program, Sir has devised a novel frequency regulation mechanism based on frequency-linked free governor mode of operation for Indian electricity supply industry. He has received Young Scientist Award by DST, Government of India, in the year 2010 for the project Integration of Distributed Generation System to improve the system reliability. He has received Vaskar Advanced Solar Energy Research Fellowship award by Indo-US Science and Technology Forum, Government of India, in the year 2015. In this program, he has worked on cost-based dynamic load dispatch in parallel converter-based microgrid. Also, he has received Young Faculty Research Fellowship Award by Digital India Limited, Ministry of Electronics and Information Technology, Government of India, in the year 2019. Above this, he has handled 9 major projects as principal investigator and co-principal investigator sponsored by DST, etc. Presently, he is one of the principal investigator to the Teaching and Learning Center on Internet of Things IoT sponsored by MHRD. He has authored many papers in many of the international journals and presented a lot of his works in many international conferences. He is a senior member of IEEE and is working as reviewer and technical advisor in many international journals and conferences. Sir, we are very glad that sir is here with us. Now I request sir to kindly deliver his technical talk. Please, sir.
Okay, thank you, madam, for kindly introducing me. And I must thank to Dr. Pratap Chandra Pradhan for inviting me. And also I'm thankful to Sushant Kumar Sethi. He is also a faculty member. So previously I gave a topic on series compensated line protection. But unfortunately, because of my health condition, I'm unable to deliver it properly. So therefore, I planned to run a pre-recorded lecture on introduction to power system automation and also SCADA system. So it will be around 1.5 hours. So please, I'm here with you and I'll just play the pre-recorded video lecture. And if you have any doubt or query, you can ask me. So thank you very much. So I'm sharing the screen. So is it visible to all of you?
Yes, sir, the sharing options.
So, because my background is from power system, so I'm also working in smart grid. So I thought, why not talk about little bit fundamentals of smart grid. So here the topic I chosen is the power system automation. So you can see here my title also power introduction to power system automation. Will not go very deep into it, but will only talk about the fundamental aspects, how it is actually implemented in the industry and how it is working in India in fact. Because as a user of electricity, many of us were not aware of how our electricity industry is working. So first of all, I will give a brief introduction of the electricity industry. Then we'll talk about more little bit how the automation happened, how the evolution took place, and how finally it is working, and what are the future directions. So already we know the automation started long back. It may, we can say it is the third industrial revolution, right? So you can see in the left side there is a automation, industry automation picture you can see here, right? There are many robots working. There is no, you will not find any person there to who are working there, right? So industrial automation actually, in fact, how this automation concept came. It is, in fact, if you'll see the natural phenomena, or if you'll observe here, you can see the right side, the solar system. Yeah? The solar system is very nicely working and very automated. You can see, if you'll see the planets, they're revolving throughout the uh, very perfectly, precisely, not colliding with each other. How it is designed very nicely, and how automated it is working, right? Very perfectly it is working. So it is also automated system, but in fact it is much more higher precisely working, and it is designed by the highest uh, highest body, or highest, you can say, the supreme personality, the supreme authority of the universe. So therefore it is designed very perfectly. And our recent development, if we'll see, the robot Sophia, right? She is one of the great invention of human being. But if we'll compare this humanoid with the real human, it is not at all at par with the real human, right? There are a lot of this because human is finally, if we'll come to the conclusion, human is the development of the God, the absolute. So therefore it is very difficult to imitate it, though it is difficult, but still we are doing it, and we are going ahead with the automation system. So therefore today's lecture is dedicated to Almighty Lord Sri Krishna, and now we'll start our lecture towards power system automation. So thank you all listeners with me, and with patience they're actually uh, waiting for this lecture. Thank you very much. So my presentation layout is we'll talk little introduction to the power system. Then we'll talk about the evolution of automation system, right? Then we'll talk about the SCADA in the power system. SCADA is the most important component in the power system automation. And then what are the advantages of SCADA after implementation, after being implemented in the power system? And then we'll see the flow of data from field to the SCADA control center, how it is happening, and then we'll conclude our lecture session. Okay, so now I'll talk about introduction to the automation, power system automation. So the main objectives of the power system to become more efficient in all respects. See, this is the phenomena, general phenomena. It is so enabling the end users to have more flexible choices. It is very essential, because we want that everybody must have flexible choices. So this is very important. End users means, if I'm talking about end users here, they are the consumers. So consumers must have more flexibility or flexible choices they should choose. And second is empowering the utilities to reduce peak demand. This is also essential, because we know that during peak demand, certainly sometimes our system becomes unstable, and sometimes it leads to blackout. So therefore we always want that our peak demand should also reduce. And third one is empowering the utilities to reduce the carbon dioxide emission. So we have to make in such a way our utility industries, so that it will reduce the carbon dioxide emission, because the objectives, the utilities are moving towards the next generation grid. So it is called next generation grid, incorporating the innovations in diverse fields of technology, right? Like we are incorporating many new technologies in order to achieve these three objectives, which are very important. One is your flexible choice to the consumers or to the end users. Second is the reducing the peak demand, and third one is to reduce the carbon dioxide emission. And therefore we are moving towards next generation grid, incorporating the innovations in the diverse fields of the technology. So power engineering today is an amalgam of latest techniques. Amalgam means it is a mixture of latest techniques. So widespread automation of power systems, especially in the transmission and distribution sector, evolved because of the following. So why we are going towards automation? The cause is the leading cause is the advances in the instrumentation, then intelligent electronic devices, and second one is Ethernet based communication media. This plays very important role, because the communication took place between different entities in the power system through this Ethernet based communication media, coupled with availability of less expensive. So as the cost is decreasing day by day, less expensive automation products. So nowadays, lot of automation products available with less price. And then the standardization of communication protocols, we can because of this standardization we can use different products from different companies, and we can cope with that. So everybody knows this industrial revolution. This is first industrial revolution which took place in 18th century, and everything was steam based. uh, Happenings are going through the stream based machines. And gradually the second industrial revolution took place in the 19th to 20th century. It is because of the invention of the electricity. Electrical energy based mass production happened during this period. Then comes the third industrial revolution, which the late 20th century, which is nothing but computer and internet based knowledge. It is because of this computer and internet based knowledge. Then the fourth industrial revolution which took place, and it is only because of more automation, because of the artificial intelligence, information technology, because of that. And this is real. In fact, it is happening nowadays. If we'll see, the whole world is now moving towards the artificial intelligence. Let us talk about the electrical energy a little bit. Introduction to electrical energy and the historical background. So we know the matter and energy, they are interconvertible, and there are various forms of energy available, right? We can see mechanical, heat energy, light energy, sound energy. They are in fact very essential as part of our life. And out of these energies, this electrical energy is very important, because through this electrical energy, which is very easily interconvertible to mechanical energy, to heat energy, to light energy, to sound energy. So therefore electrical energy plays very important role in the development of a society, or development of a country. So energy that can be converted to other forms of energy very easily, that is the electricity, right? So that is the electrical energy that can be converted to other forms of energy very easily. Production and utilization of electrical energy, that is how it happens. This production and utilization of energy, production happens through the generation, and then after transmission to the consumer end, it is through the transmission and distribution, then it is utilized at the consumer end. So this is how it happens. This is the basic background of electrical energy production. Then what is the historical background? So as we have seen that this uh, 1750 to 1850, the first industrial revolution took place when the work done by the human muscle was replaced by the power of machines. It is the first industrial revolution. Then 1850 to 1920, during the second industrial revolution, where electricity plays very important role, where the process control was introduced and the routine functions of the human mind and the continuous presence were taken over by the machines. So here electricity plays very important role along with the process control. Now how the electricity is evolved. So in 1882, the first, if we'll see the history, the first complete electric power system by Thomas Edison, and that is named as the Pearl Street Station. It is in New York. It is, even if nowadays if you'll go, if you can see it, this Pearl Street Station, it was the first electric power station, and it is DC system, DC electricity generating station. And then 1821, Michael Faraday invented the electric motor. We know everybody the Faraday's law, left hand Faraday's law, and because of that, so the electric motor was evolved, and which also played very important role in the industrial revolution. In 1884, the development of commercial DC motor took place, and it was in fact by Frank Sprague. And 1861 to 1862, James Clerk Maxwell linked electricity and magnetism, and it was also played very important role. By this phenomena we have achieved many things. Because of this, the communication system evolved, various machineries involved, electrical machines evolved, right? So then after some time, when the DC system was there, some disadvantage of this low voltage DC system was found out during the transmission loss, because of the transmission loss and the voltage drop. When there is long distance transmission of low voltage DC system, at that time the transmission loss happened and certain voltage drop happened. So therefore these are the disadvantages. So therefore in 1886, the first development of transformer and AC transmission system happened, and in 1888 in fact the development of AC polyphase system and transformers by Nikola Tesla happened. All the patents were brought by the Westinghouse. It was the company, it was a great partner of the Nikola Tesla. Then 1889, the first AC transmission line, 1889, the first AC transmission line in US, that is from Oregon to Portland, was put. It was installed. It was 21 kilometer and the rating was 4 kV. Then 1890, the debate over standardization of electric supply system took place, whether we should adopt AC or DC. Then finally the AC system won over the DC system because of the voltage levels can be easily transformed, and the AC generators and motors are much simpler and cheaper. Because of these two facts, AC system won over the DC system. Then 1893, the first three-phase line in US, that is in the southern California, 12 kilometer 2.3 kV was developed, and many different frequencies were there in use. During that time it was 25 Hz, 50 Hz, 60 Hz, 125, 133 Hz, and in fact it posed a problem for interconnection. So finally 60 Hz was adopted in US and 50 Hz in many other countries including India and UK, other parts of the European countries. Then the high voltage power transmission system was revised. Why it was revised, the high voltage power transmission? Because earlier power is transmitted at various voltage levels at 60 kV, 165 kV. So why the power high voltage transmission system was developed? Because of this, the voltage drop was less and the transmission loss was less. So that was the only cause. Therefore, high voltage power transmission was designed. So earlier power was transmitted at various voltage levels: 60 kV, 165 kV, 220 kV, 287 kV. And later it was standardized to 115 kV, 138 kV, 161, 230 kV. It is in fact in USA, it is not in India, right? So for long distance bulk power transmission, ESB system was revised and the standardized voltage at 345 kV, 500 kV and 765 kV. It is also in US, but we are also adopting this 765 kV in India. In India, the standard voltages we adopt is 132 kV, 220 kV, 400 kV and 765 kV. Then gradually the development of HVDC system came into picture. Why HVDC system came? High voltage DC system. So if we'll see the structure of high voltage DC system, at both the side of the high voltage system is AC and it is a long transmission line. In fact, it is a DC line and it is connected through the converters, high voltage converters at both the ends, and the end systems are AC. The both end we have the AC systems. Only the high volt transmission line, this transmission line is operating at the DC. So there, why it is in fact invented, let us see it. Why then HVDC system came into picture? It is because of these two facts. One is your break-even distance and other one is your synchronization of systems having different frequencies. What is this break-even distance? So if we'll plot the cost versus distance, then we find that for a high voltage AC system, the curve will look like this. This is for high voltage AC system. As the distance will increase, the cost will increase exponentially. But it has been found from HVDC system, it is exponentially decreasing. It is HVDC system, the cost is exponentially decreasing. That means your initial cost for HVDC system is very high because we are using different converters and in fact it is high voltage converters and it is very costly. And in HVAC system the initial cost is very low. Right? The initial cost, if we'll compare, it is very low. But as the distance is increasing, the HVAC system cost will increase, whereas the HVDC system cost will decrease as the distance will increase. And we'll see there is a intersection point here, right? So this intersection point, in fact, it gives us the, if we'll put a projection, this will give us the break-even distance. We call it, in technical term, it is known as break-even distance. Okay. So this break-even distance plays important role. As this distance happens, then beyond this distance, HVDC is chosen because of this cost, low cost. So there, because of this distance, because of the cost, after this, beyond this distance, the HVDC is chosen. And similarly, the synchronization of the system also plays very important role. If we'll synchronize two systems having different frequencies, we cannot synchronize with AC system. So therefore, through a HVDC system, we can synchronize it very easily. I hope everybody understood the concept. Now we can see the structure of a typical power system. So it is from starting from the generation to the transmission, then to the sub-transmission level to the distribution level. In the generation part, we can see here the technologies used are synchronous generator, induction generator, then DC generator, and whereas they can be non-renewable or renewable as well, thermal, nuclear, hydro, wind, solar, or fuel cell biomass. Similarly, your transmission system is at 400 kV, 500 kV, and 760 kV, and the technology is ESV AC system or HVDC system. And the sub-transmission level, the voltage level is 132 kV and 220 kV. And obviously, finally it will be at the distribution level, the voltage is stepped down to 33 kV or 440 volt only. So in fact, we are using in the as residential consumer, we are using 440 volt, or a single phase we are using 230 volt. So sometimes the end users, if they are industrial loads or commercial consumers or industrial consumers, they sometime in fact directly connected to sub-transmission network. So they, because at that they can directly connect to the high voltage, then they have to use a transformer to step down the voltage to consumer use. Now if we'll see the system, previously it was known as vertically integrated utility, where all the generation, transmission, and distribution, they together were with a single entity, and it was managed and operated by a single entity, and finally they give power or they supply power or the electricity to the consumers. Gradually, because of the vertically disintegration or horizontal disintegration, you can say, the generation, transmission, and distribution, they were segregated. In case of India, in fact, these three entities were with the NTPC, and gradually it was disintegrated. The generation, transmission, and distribution, they were segregated, and then finally in generation also the disintegration took place vertically, and the competition was introduced. And similarly in case of distribution also, the disintegration took place, and finally the competition was introduced. But the transmission was remained monopoly, because in case of transmission it is difficult to introduce competition because of some certain issues, right of way issues. So we cannot make the transmission competitive, or many participants cannot participate in the transmission sector. And finally we get these vertically disintegrated entities. They are Gencos having wholesale competition, Transco which remain natural monopoly, and Discos having retail competition, and finally they provide electricity to consumers. So this is the structure of the electricity system. Now how the electricity system is working, in fact, that means how the system operates. The system operation in a restructured environment after the restructuring took place. So it has two operations. Two types of model was involved. One is known as independent system operator model, and other one is known as transmission system operator model. So this independent system operator model is prevalent in America, in US, Canada, and parts of the Australia. And an independent system operator is created to facilitate competitive markets. It has the sole role to facilitate this competition. And ISO has been generally practiced in those countries wherein firstly transmission companies are also providing generation and distribution services, or equal sized transmission companies exists in the market. So independent system operator is responsible to carry out operations between the member utilities. So member utilities means they are like generators, then the distribution utilities. The ISO responsibilities include short-term reliability through balancing supply and demand, controlling voltages, managing congestion, constraints, and restoring supply after a disturbance. So this is because this is the system operator's function. Apart from above, ISO is also responsible for planning of the transmission grid from the operational point of view as well. Then we will see the transmission system operator model. It is prevalent in the whole of the Europe, part of Australia, South Africa, and also it is adopted in India. In TSO model, the operation of the grid and the ownership of the grid are integrated in a single entity which is responsible for participants. It is also responsible for the system operation functions. Neutrality is an important aspect of the TSO to ensure an efficient. So these two models are system operator models. Based on these models, actually the electricity uh, structure or electricity utilities, electric utilities are working. Now let us see various states of our system. When there is a disturbance, when there is a normal state, how the power system behaves. Now we can see under normal state, here all the constraints and the limits are under normal. It will represent this L and O. L represents the line constant and O is the operating constant. So they are not violated. They are under normal condition. So that means under normal state, the power system is operating under stable mode, under steady state condition. Now as soon as some disturbance happened, then the power system goes to the alert state. Alert state means your operational constraint is violated. I will mark it as O bar. So it is violated. Then if it is some action is taken to restore the system, then it will go back to the normal state. If some action is not taken, then finally it will go to emergency state where your L and O are violated. That means your line constant and operating constant is violated, but here it is in the emergency state. And from emergency state it is not possible for the system to go back to the normal state, to go back to the alert state or to go back to the normal state. It is not possible. Okay. So therefore it is finally to goes ahead to the in extremis state where line and operating constant both are violated. And finally from in extremis state some restorative action was taken, and after that again the normal state is achieved. So this is called the 5-state model of power system. 5-state model of power system. So this shows that when a disturbance happens, how the operating state moves. Okay. From normal state to alert state, from alert state to emergency state. So it is always there is a chance that from alert state the system can move back to normal state. If not possible, then it goes to an emergency state. Then from alert state also it is possible that the system can go directly to in extremis state. And from restorative state it can go back to alert state or it can go back to normal state. So now we'll come to our main agenda of this talk, that is the automation system. So this evolution happened gradually. The initial control equipment consisted of analog devices which were large and bulky. And the control rooms, usually very huge, having huge panels with innumerable wires running from the field to the control center. The operator could not make use of the information available, as the as during an emergency the number of events occurred simultaneously, and it was impossible to handle all of them since there was no intelligent alarming process. Excessive cost was associated with expansion of the system, the expensive space. So I am going very fast because these are all historical aspects. So we are not talking much about this. Then the expensive space requirement was also a constant during that time. And uh, storage of information, which is very important, was also an issue during that time. And as the power system, post-event analysis is crucial. If we'll store the data, then we can do this post-event analysis. Then with the introduction of computers into the automation scenario, so this in fact plays very important role. Computers, automation became more operator friendly, although initially computer use was restricted to data storage only. Initially it was restricted to data storage only, but gradually it was used to change the set points for the analog controllers as well. Then early digital computers had serious disadvantages such as minimal memory, poor reliability, programming written in the machine language, right? Then two major developments lead to the advent of the distributed control. And what are they? The advances in the integrated circuits and in the communication systems. These two in fact lead to the advent of the distributed control system. Then the distributed control system in fact were modular in structure with pre-programmed menus having a wide selection of control algorithm for execution. The data highway became possible with introduction of new communication techniques and media. Then coming to the history, how this automation system evolved, we'll first see the supervisory control and data acquisition system, which is in short form we call it SCADA system, which is widely used for automation of the power sector and represent an evolving field, the SCADA system. Detailed study of the SCADA system is essential for power automation personnel to understand the integration of devices, to understand the communication between components for proper monitoring and control of the system in general. There were undoubtedly many methods of remote control invented by early pioneers in the supervisory control field. Control probably began with an operator reading measurement. This is the first control mechanism we can say, and taking some mechanical control action as a result of that measurement. This is the first control action through, you can say, through the operator, just by taking some reading and taking some mechanical action. So most early patents in the supervisory control were issued between 1890 to 1930. These patents were granted mainly to engineers working for telephone and other communication industry. It is not for the power system. So gradually it was evolved towards the power system. As the scope of the supervisory control applications changed, so did many of the fundamentals of the supervisory control technology also changed. The supervisory systems evolved using solid state components, electronic sensors, and analog to digital converters. In this evolution, remote terminal unit, we call it RTU configuration, was maintained. The companies making the RTUs merely upgraded their technology without looking at the alternate ways of performing the RTU functions. In 1980s, the process control companies began applying their technology and technical approach to SCADA electric utility market. So as a result, RTUs used microprocessor based logic to perform expanded functions. The application of microprocessors, in fact, played a very important role here, increased the flexibility of the supervisory systems, and created new possibilities in both operation and capabilities. Automation is used worldwide in a variety of applications, ranging from gas, petroleum industry, power system automation, building automation, and also water irrigation, to small manufacturing unit automation, right? So the terminology SCADA generally used when the process to be controlled is spread over a wide geographic area. That means when we are considering a process which is widely distributed throughout the geographic system, then SCADA plays very important role in fact. SCADA systems, though used extensively by many industries, are undergoing drastic changes. SCADA systems are defined as a collection of equipment that will provide an operator at a remote location with sufficient information to determine the status of particular equipment or a process and cause actions to take place regarding that equipment or process. So in power system, we collect the information like voltage, current, power, and based on that information, the operator takes the action. So the operator is located at a particular location in the control center, and based on the information collected in the SCADA system, the operator takes the action physically. So the SCADA implementation thus involves two major activities. One is called data acquisition, that is, you can say, the monitoring of a process or equipment, and the supervisory control of the process. So these two actions were in fact taken by the SCADA, two major activities, thus leading to the complete automation. The complete automation of a process can be achieved by automating the monitoring and control actions. Automation or automating the monitoring part translates into an operator in a control room being able to see the remote process and the operator console and complete with all information required displayed and updated at the appropriate time interval. This will involve the following steps. That means the monitoring part will involve the following steps. The first step is collect the data from the field, and second is your convert the data into transmittable form. That means through some communication channel the data has to be sent. So therefore we have to convert the data into the transmittable form. Then bundle the data into packets. So then transmit the packets of data over communication media, communication channel. Then receive the data at the control center. Then decode the data. After decoding, it will be displayed at the appropriate points on the display screen for the operator. The automating the control process will ensure that the control command issued by the system operator gets translated into appropriate action in the field and will involve the following steps. So the automatic control process will have the following steps. The operator initiates the control command, then bundle the control command as a data packet, then transmit the packet over the communication media. So these are all functions of the SCADA. This is the control action in fact. The field device receives and decodes the control command. Control action is initiated in the field using the appropriate device actuation. So this is all about your control action. Now we'll see how the SCADA functions in fact. So in case of SCADA, we have, this is the power system field, you can say, right? So this is power system where there are many equipments and there are many measuring equipments or sensors, you can say, right? So they are called the measuring elements, and they are also called sensor or transducer relays. So the measuring elements, that is like voltage transformer and current transformer, they are called CTs and PTs. They are the measuring elements. PTs, potential transformers or voltage transformers. So they will in fact feed information to the sensor or transducers. They are called the relays, and the relay will feed the information to the RTUs, that is interfaced with the AD converter, and RTU will feed the data to the communication channel in the transmittable form, and then it will reach to the master station or computer system. It is the collection of data. So this part of left hand side is it involves the collection of data or information. Collection of information. Okay. And if we'll see the right side, it involves the control action. The master station sends the control action through the communication channel, and it was converted through digital to analog converter. Then it gives command to the controller or actuator, then to the controlling element in the power system. So this involves your control action. Okay. So this is all about your SCADA, the basics, the fundamentals of the SCADA, how we collect the information from the system and we take the control action. Monitoring and controlling process. So then coming to the components of the SCADA. So SCADA is an integrated technology composed of the following four major components. So these are the four major components. One is called the master station, and your communication system is there. Then RTU or IED, that is intelligent electronic devices. Then the field equipment. The field equipments are relays and the CTs and PTs. They are the field equipments, right? And they are in communication with RTUs or IEDs, and RTUs feed information to the master station through the communication channel. Another thing is the human machine interface, through which the human can be interfaced to the machine. That is the console. We call it console. So first part is RTU. RTU is, it is like the eyes and the ears. Okay, eyes and the ears of the system, and also it has hands, like in case of human body. You can see in the human body picture here, right? So it collects signal from the field and processes and sends to the master station here. So like in human body, the sensors are eyes and ears, right? Eyes and ears. And as soon as we get the sensing signal, it goes to the brain. Here brain is nothing but the master station. And the brain then gives the signal whether to eat, gives the signal to the hand, and the hand actuates the control action. So the master station sends the control signal to the hand to act. So today, the intelligent electronic devices are replacing the RTUs. So there are more intelligent devices coming into picture, and they are replacing the RTUs. The next part is your communication system. This refers to the communication channels employed between the field equipment and the master station. So this in fact the communication channel between the field equipment and the master station. The bandwidth of the channel limits the speed of communication. Everywhere bandwidth plays the major role. Then master station, this is a collection of computers, peripherals and appropriate input-output systems that enable the operators to monitor the state of the power system or process and control it. Then human machine interface, this is in short we call it HMI. It refers to the interface required for the interaction between the master station and the operators or users of the SCADA. Let us see the SCADA in the power system. SCADA systems are in use in all spheres of the power system operation, starting from generation to transmission to distribution and to utilization of electrical energy. So SCADA functions can be classified as basic and advanced application functions. So in power system it is classified into two types. One is for basic function, other one is for advanced function. So the basic SCADA functions include the data acquisition, remote control, human machine interface, historical data analysis and report writing, which are common to generation, transmission and distribution systems all. And the SCADA applications, if we'll see the application functions, these are the basic functions. If we'll see the application functions, here are the application function. The SCADA system, the application function is substation automation, which has two limbs. One is the SCADA automation generation or control, then the distribution automation, right? And if we'll go to the more advanced function, it was energy management function or energy management system. Here also in the left side we have distribution management system. Generation SCADA application function, in addition to the basic function, it includes the following application functions. The first is your automatic generation control. It is a compendium of equipment and computer programs implementing closed loop feedback control of frequency and net interchange. So this is also in fact it is very important. Economic load dispatch calculation, the scheduling of power from all available sources in such a way to minimize the cost within some security limit. Then interchange transaction scheduling, it ensures that sufficient energy and capacity are available to satisfy load energy and capacity requirements. Then transaction evaluation, it evaluates the economy of transactions using the unit commitment results as the base condition. This is generation function. This is also unit commitment is another function. It produces the hourly startup and loading schedule, which minimizes the production cost for up to 1 week in future. Then the short-term load forecasting, it produces the hourly system load for up to 1 week into the future and is used as input to the unit commitment program. Then hydrothermal coordination, the scheduling of power from all available hydro generation in such a way to minimize cost within constraint. So these were all generation automation function. Now we'll come to the transmission SCADA application function. So the transmission SCADA will include the energy management system functions such as the network configuration or topology procedure. It analyzes the status of the circuit breakers as well as the measurements to automatically determine the current model of the power system. Then the state estimation, this is very important. It provides means of processing a set of redundant information to obtain an estimate of the state variables of the system. Then contingency analysis, it simulates the outages of generating units and the transmission facilities to study their effect on the bus voltages, power flows, and the transient stability of the power system as a whole. So there are many applications. In fact, I think many of you might not be understanding this because these are all power system aspects, and if we'll go deeper into it, it will take more time, so therefore I am skipping this. So three-phase balanced power flow, it obtains complete voltage, angle and magnitude information for each bus in a power system for specified load and generator real power and voltage conditions. Then optimal power flow, it optimizes some system objective function. So like we can see here, such as production cost, losses and so on, subject to physical constraints on the facilities and observation of the network laws. Then we'll come to distribution automation application functions. The distribution automation or distribution management system include the substation automation, feeder automation, and customer automation. The additional features incorporated in the distribution automation will be fault identification, isolation, and service restoration, the network reconfiguration, load management or demand response, active and reactive power control. Then power factor control, this is very important. And short-term load forecasting, three-phase unbalanced power flow, interface to customer information system, then interface to geographical information system, GIS, then trouble call management, interface to outage management systems. So this is all about your, we talked about the functions, okay, functions of SCADA functions in generation, transmission and distribution. Now we'll see the advantages of the SCADA in power system. So what are the advantages? Advantage is automating a system brings many advantages, and the case of power system is no different. Some of the advantages like increased reliability, as the system can be operated with less severe contingencies and outages are addressed quickly, lower operating costs as there is less personal involvement due to automation, faster restoration of power in case of breakdown, as the faults can be detected faster and the action can be taken faster. So better active and reactive power management as the values are accurately captured in the automation system and appropriate action can be taken. Reduced maintenance cost, and the maintenance can be more effectively done. The transition from time-based to condition-based maintenance with continuous monitoring of the equipment. Then reduced human influence and errors, so therefore errors are also reduced as the values are accessed automatically and the meter reading and related errors are avoided. Faster decision making as a wealth of information is made available to the operator about the system conditions to assist the operator in making accurate and appropriate decisions. Optimized system operation as optimization algorithms can be run and appropriate performance parameters chosen. Okay, so this is all about your automation. I think the time is going to over. So we'll not talk about these things because this will take more time. I'm going to directly conclusion page. These are all about the sensors we are going to use, or nowadays it is being used in the power system field of the power system application. So relay, then there is various different sensors, PMUs, right? So we'll not talk about more about this synchrophasor fundamentals. So as I thought, so now we'll talk about the flow of data from the field to the SCADA control center. So we can see here, this is your field where the bus bar voltage is, let us say the bus bar voltage is 220 kV here, and it is to be fed to the RTU through the potential transformer and through the voltage transducers. Okay, the potential transformer, it in fact measures the voltage uh, phasor, and it feeds to the analog to digital converter, and which is an intrinsic part of the RTU. And then RTU, after it is converted to the digital form, then the data packets were formed, and finally the data packets were sent through the communication channel, and then after, through the communication channel, it reaches the control room, and where the master station is there, and where the personnel there takes the control action. So now we'll talk about in India how this SCADA system is implemented and how it is working. In India, we have the 5 regional grids. If we'll see here, the northern regional grid having different states: Jammu Kashmir, Himachal, Punjab, Uttarakhand, Uttar Pradesh, Delhi, Rajasthan, right? And similarly, we have other regional grids. We have northeastern regional grid, which is here, and then eastern regional grid, which is here, consisting of Bihar, West Bengal, Jharkhand, and Odisha. Then we have western regional grid here. This is your western regional grid, which is consisting of Madhya Pradesh and Maharashtra, Chhattisgarh, Gujarat. Then we have southern regional grid, which is consisting of all southern regional states: Telangana, then your Andhra Pradesh, then Tamil Nadu, Kerala, and Karnataka. So if we have 5 regional grids, and we'll see how the SCADA operates in these 5 regional grids. We can see here the structure of the SCADA in the India. So we have the master station here, which is located at NLDC, that is the National Load Dispatch Center, that is located at Delhi, right? National Load Dispatch Center. And this is in fact, we can say, the master station, and which is communicating with other SCADA centers or other control centers or SCADA centers, you can say, right? We can see here there are 5 other SCADA centers or control centers equipped with SCADA in each of the regions. Like in ERLDC, we call it Eastern Regional Load Dispatch Center. In Northern Regional Load Dispatch Center, Southern Regional Load Dispatch Center, Western Regional Load Dispatch Center, and Northeastern Regional Load Dispatch Center. So these load dispatch centers are located at a particular location. Like if you'll see the Eastern Regional Load Dispatch Center, it is located at Kolkata, and Northern Regional Load Dispatch Center located at New Delhi, Southern Regional Load Dispatch Center located at Bangalore, and Western Regional Load Dispatch Center located at Mumbai. The Northeastern Regional Load Dispatch Center is located at Ceylon. So these centers, having equipped with SCADA, they interact with different SCADA center or different load dispatch centers at individual states in their region. Like they will interact with the respective state load dispatch centers, which is also again equipped with the SCADA. And similarly, these regional load dispatch centers also in interaction with the respective CT substation. CT means your central transmission utility. Central transmission utility. Okay. So and also it is in with respective central generating substations. Then the state load dispatch centers, SCADA centers, are also in interaction with the state generating stations, substations, and the state transmission subs. So if you'll see the system, there are many control centers distributed throughout the country, and they are interacting with each other, and they're collecting data from the field, and they're sending information, and they're taking control action very easily. So we can see how many SCADA centers, how many control centers equipped with SCADA. There are lot many, right? So they are working together. In each state, we have SCADA system. We call it state load dispatch center, right? So now I can conclude with this. So the conclusion is we have discussed the role of SCADA in automation of the power system, and also we discussed the energy management system structure in power system along with the SCADA, and we talked about we skipped this because of the uh, time factor. We don't have much time to discuss about the PMU. In fact, this PMU plays very important role nowadays in SCADA, right? And this is PMU means this is called phasor measurement unit. We didn't talk about this much. Measurement unit. And then we talked about the structure of SCADA system in Indian power system, right? In the references I took, this is one of the book. So major SCADA in theories I took from this reference. This is by Minnie Thomas and John D. MacDonald, CRC Press, 2015. Then Wikipedia, Google, and PGCIL India. So thank you very much for your patience hearing.
So, any questions from our participants? Are you there to answer? Any question from our participants? So, I think no questions. Now, on behalf of our FDP committee, I extend my heartfelt thanks to our revered speaker, Professor Dr. Sanjay Kumar Parida sir of the Department of Electrical Engineering, IIT Patna. Although sir is not well, since sir spare his valuable time and talk through his beautiful presentation. Thanks a lot, sir, for accepting our invitation and
Thank you.
presented elaborately in the theme area and enlightened to all our
Okay, thank
participants.
you. Thank you.
And thank you, sir. As per the feedback from our participants, the whole session was marvelous and informative one, and we have no words to express. Thank you, sir, for your joining and kind association, and expecting more sessions in the
Thank
near
you.
future. Now it's time of felicitation to our esteemed speaker of the session. May I request our coordinator, please share the screen of felicitation. Swaroop, share करो. हो नहीं गई. Just a minute. With enormous pleasure, DRIEMS Autonomous felicitate Dr. Sanjay Kumar Parida, Associate Professor, PhD, IIT Kanpur, enlightening the FDP on Smart Grid Technology, SGT 2022, as an expert talk on 4 January 2022 on virtual mode. As a dignified academician, Dr. Sanjay Kumar Parida stands as an epitome of knowledge. Thank you, sir.
Thank you. Thank you. Thank you. Thank you, all of you, all organizers, coordinators, and organizers of the program. Thank you very much.
Thank you, sir. Thanks to all organizing committee members for successfully organizing the session, and thanks to all participants for joining and patience hearing. Thank you all. And participants are requested to fill the feedback link followed by the quiz test. Thank you all.